So, so we talked about how we take a force and we move it through a distance, and that's work. And we talked about power, right? And we said that power was how much work we do in a given time. And physicists tend to talk about energy because we want to know, is it possible? Whereas engineers want to talk about, is it possible today? So they talk a lot more about power. So power is really more useful a number than energy is. And then we talked about mechanical energy. When you do work on an object using your pushing force, then that object gains mechanical energy. It doesn't weigh more. It doesn't look any different. It just has a couple of things could be happening. It could be higher in the gravitational field. We put it on a shelf. We push it uphill. And if we let it go, it can come back. So that energy is stored in it. Or it goes faster if we're pushing on level ground. Or if we're doing a bit of both, up a hill but not a really steep hill, it could go faster while going to a higher height. But whichever way you look at it, that work, we say it manifests itself. It shows itself in that object somehow. And so we define from that potential energy, and we define kinetic energy. And then we say, well, you know, kinetic energy and potential energy are two forms of mechanical energy. There's another form which is spring potential energy. You could push against a spring, and then the spring would spring back on you if you let go. But we don't talk much about it in this course. But in physics, general physics, we talk about spring potential energy. It's enough we've got at the moment. And then, so there's some games we play where we say, we take an object like a pendulum, and we can say, it's got this amount of kinetic energy now, it's got this amount of potential. Let's do some of those. Let's just, for a minute, let's just do a couple of those. Oh, and this is the classroom where I can't do some of those, so I'll do it down here. So let's come along here. Let's find my pen. Let's come along here. Good. Let's find my ink color. So where are you, pen? There you go. Let's find my ink color. Let's do, I feel green today, so we'll do that. So here's a pendulum. Pendulum swings backwards and forwards. Let's say here's the pendulum. And at this point, I say it has 10 joules of kinetic energy. So it's moving. And it's got 5 joules of potential energy. So I could say, what's its mechanical energy? Mechanical energy is just equal to, just add those two together. So it goes 15 joules. Because you got 10 and 5, get them together. I could come over here and I could say, well, now I've only got 2 joules of potential energy. So how much kinetic energy would I have? And for that, I say, well, hold on. We've still got 15 joules, because once the mechanical energy is in there, it's not added to or taken away from unless there's a force acting on it. So it's like trapped in there. And so I've got to have a total of 15. If I have 2 as potential energy, I have 13 as kinetic energy. Okay? It's as if when you put money into your bank account, the bank decides, oh, we'll put it all in checking. Oh, we'll put it all in saving. Oh, we'll put it all in checking. Oh, we'll put it all in saving. And they just move it backwards and forwards. And you say, well, you still got as much as you always had. We're just moving it from one account to another. That's what nature does with mechanical energy. It says, I'm going to put it all in kinetic. No, I'm going to put it all in potential. And it does it a certain rhythm. It's kind of a most amazing thing when you think about it. Why on earth should a pendulum keep swinging backwards and forwards? From an energy point of view, it's just transferring the energy from one form to another form, one form to another form. And it does it at a certain speed, with a certain rhythm, because of the nature of the situation. Yeah.
Oh, that's what I was getting. What determines the speed?
So it depends on the physical situation. For a pendulum, it turns out it's the length of the string and the pull of gravity. So if you take that same pendulum to the moon, you'd have a different speed of oscillation. Okay? Because you change gravity. If you change the length of the string, you would have on Earth a different swing rate. It does not depend on the amount you move it to the side. And that catches most people out. Most people think if you move it further to the side, it must take longer to go backwards and forwards because it's got further to travel. And it turns out it goes faster. So it kind of like, it makes up for itself. And it does not depend on the mass. And that's really weird. You think that a big, heavy thing. In physics, we teach people all the time, more mass means more inertia, means sluggishness. And yet in this case, because the mass determines the weight, which is the pull of gravity, and mass determines the inertia, the two effects cancel each other out. So it depends on the length, depends on g. If it was a mass on a spring, then it would depend upon the strength of the spring and the mass, not the length of the string. So it's kind of like different things have different contexts. You know. So then the next thing we want to talk about is, I find it kind of fascinating, and it's not actually done in general physics, which is simple machines. Basically, so our problem, going back to what my brother said about you guys care about energy rather than power. The other problem with only caring about energy is that all jobs are possible. I can do anything. Just give me time. I can do it. You want me to dig the Panama Canal? I'll do it. It'll take me a long time, but I can do it. It's a huge job. I can do it. Well, realistically, I can't because I don't have enough time. And there's other things that I can't because I'm not strong enough. So you want me to pull down that tree? In principle, I can do it. I can apply a force and pull down that tree. But in practice, I can't. And so it's not that I've not got enough energy. It's that I don't have enough strength. And so along came the invention of simple machines. And simple machines are amazing because they enable a small force move through a big distance. That's work. To do the same work as a big force moves through a small distance. So if I want to lift up this trolley, then, all right, how far do I want to lift it? I want to lift it by about, 5 inches. Okay. I need a certain force through a certain distance. That's a certain amount of work. If I lift that trolley by 5 inches, that's a certain amount of work. And the problem is, I certainly have the 5 inches, but I don't have the force necessarily. So a simple machine says, oh, okay, you're not strong enough to lift that trolley. So I'm going to cleverly make a scheme where you're going to do the same amount of work you need to do, but I'm going to let you pull further with a smaller force. All that work is a force through a distance. If I don't have enough force, I can use a smaller force with a longer distance because it all balances out in the end. So they're just very clever, and the simplest one is probably just a fulcrum, a lever. I have some kind of pivot point, and then I have something a force I need to move. I want to move this barrel upwards. It's a force I need to move. And I'm not strong enough just to lift it. So what I do is I put a lever here, a little distance, and a big force is the same as a little force and a big distance. So this is D, and that's F, and that's D, and that's the lifting force is F. So I get a big force moved over a little distance is the same as a little force moved over a big distance. You see how that kind of like symbology works? That symbolism. So it doesn't matter as long as the product is the same. So by having a big lever arm and a small lever arm, I can use a little force to move a big thing. And in fact, at places like the Chicago, the MOSI, like the Museum of Science and Industry, like we have one on Fowler Avenue. There's one in Chicago as well, and they actually have a car on a big girder. And basically kids come along and kids kind of push down on the girder and the car goes upwards, and you say you just lifted a Toyota Corolla, you know, little kid lifting a Toyota Corolla. Quite capable of it. What they're not capable of is having the force necessary to lift it, but through a big distance they can do it. If you go to Mosey, if you go to our Mosey, there's this device, and it has like 2 ropes. And if you look, one rope is attached like there, and the other rope is attached there. So your mums and dads are pulling on this side, and the kids are pulling. I can't show it properly, but so the kids are pulling here, and the mums and dads are pulling here. And what happens is the kids can out-pull the mums and dads because they're pulling further away, and they pull. So this thing moves further than this thing does, so they can outperform the parents. This kind of makes them feel really good. It's a clever lever, you know. So a lever is a simple machine. A ramp, actually, is a simple machine. If you think about it, yeah, the amount of work is your lifting force through that distance. Well, I'll substitute it for a sliding force over a longer distance. Inclined plane, a ramp. Take a ramp and wind it around a building, and you have a spiral staircase or a spiral ramp. That's just a ramp that goes a long way around in a circle. What does that look like? If I do, what does that look like?
A screw.
A screw. That's a simple machine. Sideways turning enables you to put an awful lot of force going inwards. Big distance, small force, little distance, big force. So it's very clever. And then we get some with pulley systems. So this is a simple pulley where, and if you think about it, this might not be obvious, but if I want to raise this block by 1 foot, how much do you think I have to pull that string by? Is it 1 foot, 1 foot? Or do I have to pull more than 1 foot for this string to make this go up? And think about the strings on both sides, the strings on this side and the strings on that side. Can you guess? What do you think? How much string do I have to pull to get that to go up by 1 foot? It's double, isn't it? And that's not, I didn't find that obvious. So I ended up getting one and trying it. And it's like, you can do it with paper towel and, you know, at home. But, so there's a 2-to-1 ratio just on that pulley. And then you go, well, hold on. If I have 2 sets of pulleys and I have it loop over one, loop under the other, loop over the other, I can get much bigger ratios. Now, you don't need to, there is a way you can figure out from the number of pulleys the ratio. It's called the mechanical advantage. I don't really care about that. What I care about is if I tell you how far you pull, and I tell you how far you rise, and I tell you what the force is, can you tell me how big the force you need to pull with is? So I'll give you the mechanical advantage in terms of the different distances, not the number of pulleys. So it's not as complicated as it could be. So the equation that you're going to be thinking about all the time is this guy. The force on one end times the displacement on one end is equal to the force on the other end times the displacement on the other end. That's where I want us to go on this. So here's an example. A block and tackle, that's what this is called, is used to lift a box weighing 20 newtons. So this is 20 newtons. Through a distance of 3 meters, so that's 3 meters. This is achieved by pulling the rope through a distance of 6 meters, so that's through 6 meters. What force was applied to the rope? How hard did you have to pull? So you don't really need all these different pulleys on. You just have, and you just have it, you can just think of it like that. And if this is a weight of 20 newtons, what do you think the lifting force will be. I'm going to go really slow. I'm not going to accelerate. So if it's the same, if it's in equilibrium, if it's just moving steadily, it's in equilibrium. So the same force up as down, yeah. So my lifting force will be 20 newtons. And my lifting force on my displacement here is going to be 3 meters, yeah. So that's how much work my machine, well, I am doing through my machine, yeah? And then which is the bit that I actually do? Well, I have, this is 6 meters. And here's my force. So I know the work on the left-hand side is equal to the work on the right-hand side, because there's no engine in there, and there's no friction to speak of. So I say, well, my force times my distance is equal to my force times my distance. I call them 1 and 2. Could have called it left and right, up and down, doesn't matter. So I look at my diagram and I go 20, and the distance was 3. Remember what it said? You lift a 20 Newton box through 3 meters. And this is going to equal my force, which is what I want, times my distance, which is 6. So I'm going to say 60 over 6. Actually, 20 by 3 is 60, divided by 6 is 6, is equal to F2, which equals 10 newtons. So a 10 Newton force pulling here lifts a 20 Newton force there. I got to pull it twice as far, but it can be done. Yeah.
Yeah, I think your calculation is right, but the picture that you showed is wrong.
Which picture? This one down here?
Yeah. Because if you show like that, then you just change the direction, not the force.
Oh, so yeah, so that's exactly right. It won't work for a single pulley. But what I'm saying is, don't bother trying to draw the complete pulley. Maybe what I need to do is I need to put this like in some kind of housing so you can't see all the pulleys. You're right. For a single wheel it won't work. But I'm saying take all that and just represent it like that. Don't try and draw it on your diagram. It's going to make it really complicated. But you're right. You're perfectly right. You can't have a single wheel. It's got to have some complex mechanism. Yeah? So, can you do this one for me? Can you click in and do the next one? And just give me a second, because wouldn't you know it? So let's just bear with me 1 second. So do that. You can't click in yet. Hold on. I got to get rid of that. I got to come down here. I thought this was on, and I can't have clicked it on. So there it is. Okay. So now I'm going to come along here and go like that, and go from the beginning. And why is it not there? Bear with me 1 second, please. Sorry. Let's move you somewhere. You're on. I'm going to put you on there so that you go in, and I'll try this again. And I can't see you again. And I don't know why I can't see you again. Well, let's just click in, and then we'll see how it goes. I can do this if worst comes to worst. Will you let me go down? No, you won't, will you? Yeah. Oh, that's what I can do. Go back here. No. I'm done. Okay, let's see what the answer was that people got, and then we'll just. So let's have a look. Let's. Any more for 12? We've not got that many people here today, so stop it. Let's do this. Everybody's saying A. So now let's look back at our answer and see if that's going to work. So, so people are saying A, so let's have a look. So we have our, now let's start again. Let's do, oh, it's down here. Yeah. That one. Oh, man. It's going to be one of those days, isn't it? Let's go here. So, again, we have our kind of machine. I'm going to draw it like that, and I have my thing coming down. Then I have my rope coming here. And we say a block and tackle is used to lift a 15 Newton weight. Oh, that's interesting. 15 newtons. So my lifting force, if I go slow, is 15 newtons. And it goes up a distance of 2 meters. And then it's achieved by pulling, so this is now 6 meters. And I want to know what my force is. So I say my work on the left is equal to my work on the right. So I can say my F left, D left is equal to my F right, D right. So I look at my diagram and I go 15 times 2 is equal to, and it's going to be F right times 6. So that's going to be 30 over 6 is equal to F right. So F right is equal to 5 newtons. And there it is. Yep. Yep. Lever is used to lift a box weighing 30 newtons. So if that's weighing 30 newtons, then my lifting force must be 30 newtons. And the distance, through a distance of 2 meters, so that's 2 meters. So I want my 30 newtons through my 2 meters. This is achieved by pushing the lever handle down through 12 meters. So this is 12 meters. So it wants to know what the force is. So I say W left is equal to W right. F left, D left is equal to F right, D right. I just need to take these two guys. So I'm going to say 30 times 2 is equal to F right times 12. So 60 over 12 is equal to F right. So F right is equal to 5 again. Okay, just for coincidence. And so on. Okay, so that's how you do these things. Let's change pace a little bit, and let's have a look at this next thing. The next thing is efficiency. So we have machines, we have people, we have whatever, and they can actually do work, but there is friction. Okay. So what I get out is not necessarily what I put in. And so I can characterize that by efficiency. The lower the efficiency of the machine, the greater the percentage of energy that's converted into heat. Friction is the real issue with our universe, because when we have a mechanical system and it has friction, we start losing mechanical energy. Mechanical energy is conserved in the absence of friction. When there's friction, it goes to heat and it starts forming thermal energy, and it's a different bank account completely. So we say that thermal energy steals our mechanical energy and makes it into thermal energy. And in fact, when you get in your car and you're driving to work, the vast majority of the energy that you burn is overcoming friction. And all that work ends up heating up the environment. That's in part why, if you're by a main road, it's a bit warmer than it is elsewhere, because, you're converting that chemical energy into mechanical energy. That mechanical energy through friction becomes heat. And in fact, if you look at sort of globally or from a universe point of view, Your stars are nuclear, and they're creating energy, light energy. Your light energy comes to Earth, and through biosynthesis creates fossil fuels and trees and the like, chemical energy. You then get that chemical energy and you burn it using combustion. Goes into, if you like, chemical energy, and it becomes heat for a little while. Then you use that heat to do mechanical work, and then that mechanical work gets converted into heat. So the sun's energy, which is concentrated, gets changed into various forms which are useful. And then we get it to do a job we want, like taking me to work. But it's as if the sun had just shone and I hadn't gone to work. The universe doesn't care if I get to work or not. Only I care if I get to work. But the catch is, once the energy is spread out like it is when you heat up a planet, it's not useful anymore. You can't really make it into a source of energy. So we say it's degradation of the energy. It's still there. The same amount of energy that was there is still there now. It's just spread out. It's gone from the sun to the various planets. And it's warmed the planets a little bit, but not enough to be useful. Meanwhile, the sun's running out of its fuel. So it's a bit depressing, really. You get to the stage where eventually they believe the universe will be just bits of atoms with no energy, just sitting in space. Maybe potential energy, because then they're orbiting, but nothing much to speak of. You won't see stars. They'll all have burned out. It's going to be... I'm kind of glad I'll be gone by then, but I'll be gone way before that happens. So efficiency can go from 0 to 100%, and we can also talk about it as going from 0 to 1. So there's two ways of talking about efficiency. There's talking about efficiency as this fraction, convert it into a decimal, or we can have efficiency is equal to what you get out over what you put in times 100. And actually, I'm sorry, with the way this is my loose terminology. I'd actually say, because you can put work in and get energy out, actually. So we could have energy out over work in, or I could put work in and get work out. So don't be tied to this W meaning work and this E meaning energy. Think of energy as work has been interchangeable. I don't want to write down 4 equations. So we say a motorcycle does 50 joules of work and consumes 100 joules of energy. So my what I get out, I'm going to say my work out is equal to 50 joules, and my energy, in this case in, is equal to 100 joules. So it says, what is the average efficiency? Efficiency equals, well, it's what I get out, which in this case is work, over what I put in, which in this case is energy. And if I want it in percentages, I got to times that by 100. So energy is equal to, let's have a look. We said 50 over 100 times 100, which is 50%. And they're like that. That's how you do them. This next one, 60 and 240. Motor does 60 joules, so the work out equals 60 joules, and the energy that you put in is 240 joules, so my efficiency equals work out over energy in times 100. So efficiency equals 60 over 240, which is like 6 over 24, which is like 1 over 4, which is like 0.25. Oh, got to multiply by 100 times 100 times 100 times 100 times 100, which equals 25%. So I changed it around on the last one. A motor E equals 25%. How much work can it do while consuming? Energy in is equal to 80 joules work out. So all we do is we say, okay, work out over energy in times 100 is equal to my efficiency. So I can say work out over energy in was 80 times 100 is equal to 25. So I say my work out is equal to 25. Multiply both sides by 80. Divide both sides by 100. That's like 80 over 4, which equals 20. And it's work, so it's going to be joules, 20 joules. Now, I don't know what you feel about this. Supposing that I'd said to you, oh, 25%, that's a quarter. Oh, 80, what's a quarter of 80? That's 20. Is that more accessible? For some people, that's just more accessible. It's like, hey, I know that. I can just do that in my head. But doing all this stuff with the equations drives me crazy. And for other people, it's like, I can't do that in my head. I keep getting it backwards, but I can do it with the equations. So you find what works for you, you know. And then we have a couple of things. We have, so recycled energy. Recycled energy is the re-employment of energy that otherwise would be wasted. For example, a typical fossil fuel power plant discards 2/3 of the energy produced from the fuel as waste heat. Think about it. You go down to Big Bend Power Station, okay? For every 3 cars of coal that comes in, I don't think it burns coal anymore, but let's say it's coal. For every 3 cars of coal that comes in, 2 of them are just wasted. They're just heating up the environment. Not only is it wasted, but we've actually got to pay to cool the effects of it. So 2/3 not only is not useful to us, it damages our environment. And there's no real way around that. That's just the efficiency of those machines. You can't really get around that using that technology. Now, in Britain, it's the same as here. Britain's power stations are very similar. They're in the countryside or in the suburbs, and they're big. You can see them for miles. And they have these big cooling towers, like Big Ben does. And the electricity comes on wires, and you could live in a housing project and never even know where the electricity is from. You might. From my house, I couldn't see the generator. From my school, I could. One city had basically 2 power stations, one for one side, one for the other. Okay. Europe went another way. What Europe said was, this water that so what happens to the waste heat? Basically what happens is, in order to get the energy from the coal to the turbine to make electricity, use steam. That's water. And when steam loses energy, it turns back into water. But it's not cold water. So it did the useful bit of generating electricity, but it's still got 2/3 of the energy. And if you try and get that extra energy out, man, it slows down the whole process. So they throw it away. They basically put it in the cooling towers to cool. So because of power, they give up efficiency. And they make it so that the heat is lost. What they did in Europe was they said, that's useful energy. That could heat homes. That could be used in agriculture. That could be used by people. So we don't want to build a huge power station in the middle of the city because it's going to be unsightly and people are not going to like it. And besides, you can't take the water that far before it cools down. So it's not like Tampa could have one power station giving us all hot water. That wouldn't work. But we could have a little power station in every subdivision. And that little power station could look like a normal building. Doesn't have to have steam coming out of it, because we're going to use the water to heat. The reason why steam comes out of a power station is because you're trying to get rid of that heat as quickly as possible. Hey, we want that heat to go to people's houses. So they can build a building that looks like just a two-story building, and it can not only give electricity to that local community, but it can also give them free heat. Now, for Florida, you know, we don't necessarily need free heat. But can you imagine what it's like in Buffalo, New York? Free heat. Or even better, they can charge people for the heat. I mean, you know, hey, give it away or charge something for it. In Holland, what they do is they take that heat and also the carbon dioxide that those fossil fuels produce, and the farmers want the carbon dioxide because it's really good fertilizer. So they have these greenhouses, and they heat the greenhouses using free or cheap electricity, cheap energy, cheap heat from the power station, and they use the carbon dioxide to help the plants grow. And they said, we don't want one without the other, we want both of them. So they in Europe, there's some power stations, some power systems, and they're getting 90–95% efficiency. They take it really seriously. And there's this thing called cogeneration or basic recycling, which basically enables them to do this. And it's just not our tradition. It's not Britain's tradition. It's not the US's tradition. And so trying to get our local power companies to design a housing system with a little power station inside it's a hard task. But in Europe, they just do it all the time. Is another advantage. So when we have a hurricane or we have some kind of problem, the distance between my house and the power station is probably 20 miles. And if one of those wires comes down, I got no electricity. Yeah? I mean, a tree falls on a wire, I got no electricity. And if that power station gets flooded, none of us have electricity. Okay? So if there is a, natural disaster, it can affect an entire city, or half a city at least. With these little power stations, what happens is one of them's down, you don't notice it because they're all interconnected. So that one goes down, we'll just move the power around. That one goes down, we'll just move the power around. Bad weather over there, we'll just move the power around. So it might affect, if you're relying on the water from the power station. Yeah, if the power station's down, you might not get the free water. But you can still get electricity. It's just a different approach. So more and more, as we go on, energy becomes a problem, and so does water. It turns out that something like 50% of New York City's water is used on power stations. They take it in, they heat it up, and then they have to somehow try and cool it. It used to be they would build power stations on bays, like Big Bend is built, or on rivers, because it was a free supply of water. And they'd take water in, and they'd heat it up, and then they'd discharge it. And they started killing all the fish, because they don't like to be in hot water. So then biologists said, hey, you're killing all the fish. And they said, well, what do you want us to do about it? Well, we want you to not put out such hot water. So now there's laws about you can't have more than a 15-degree rise in the temperature of the water caused by a power station. And that helped, but it still affects the ecosystem inside. And so now they have a rule for new power stations. They can't use natural water supplies. You can build a little lake, and you can feed backwards and forwards to that lake, but you can't just go into an estuary, or you can't go into a river, because it was just too damaging. And, when I moved to Florida, there were half as many Floridians as there are now. So if it scales, there were half as many power stations as there are now. And if you scales, there was half as much damage as there is now. And if it scales, you get to the point where you're significantly affecting your state just by increasing the numbers. So by having these rules saying you can't do that anymore, it might seem inconvenient at first, but it means that the waterways can be unaffected by the increase in population. So this recycled energy, I think, is a really good thing. So, for example, typical fossil fuel plant is only 2/3 of the energy produced from the fuel as waste heat. The waste heat is only waste heat because it is discarded. It could be used by nearby homes and factories, and Europe has successfully done this. There's a really good film called What Are We Waiting For? And that's this guy. So if you click on it, you're going to have to copy it down from the notes and click on it. It's a really good film. It's maybe 30 minutes long, and it goes through all this stuff about what's going on in Europe. But recognize that if we could make the power station down at Big Bend 100% efficient, our electricity bills should be about 1/3 of what they are. It's not that, oh, they're wasting that energy, that's bad luck for them. It's that they're wasting that energy and we're paying for it. You know? I mean, imagine all those trucks of oil or coal or whatever that have to pull into that plant, and effectively we just waste them. 2/3 of everything comes in, we just waste it. By the way, typical gasoline engine, about 30% efficient. So also 2/3 of the gasoline you put in your car is just wasted. And then energy for life. And what I'm trying to get across here is there's a food chain. For example, we eat fish, the fish eats worms, and the worms eat decomposing vegetation. So in a way, we're eating decomposing vegetation, and we're eating worms. I mean, you know, we're not, but they don't look like worms, but the energy from the worm becomes the fish, and the energy from the fish becomes me. It's kind of a bit weird when you think about it. The problem is it takes a lot of vegetation to grow a worm, and a lot of worms to grow a fish, and a lot of fish to grow a person. So meat is great, and fish is great, but it's incredibly inefficient as an energy source. The fact is that people who eat animal flesh are getting food energy in a very poorly efficient way than people who simply eat vegetables. As the developing world catches up with the developed world, food choices change. Meat becomes a greater part of the country's diet. And so ironically, it's kind of, in a way, it's so ironic. It's like you take countries which are, in terms of gross domestic product, are poor, and as they economically develop, they move towards a less efficient way of sustaining themselves. And, you know, I mean, that's not for us to argue about. I mean, we eat meat. It's like, as a society, there's a trade-off. It's like, you know, for many years I was a vegetarian until I realized that I was just substituting. I ate bread. I didn't come from a vegetarian tradition. I came from a meat and potatoes tradition. And so when I stopped eating meat, I ate more potatoes. I mean, it was simple as that, really. Bread was the thing. And so I was eating carbohydrates and eating carbohydrates and eating carbohydrates. And as I got older, it began to catch up on me. And so I was getting to the stage where, you know, you reach your late 50s and your 60s and your diet does start mattering, and I was putting on a lot of weight. And my wife, who's not a vegetarian, said, just, you know, you used to eat chicken years ago. Just eat some chicken. I read a book, basically, about nutrition, and they said, you know, hey, don't be a bad vegetarian. You know, be a good vegetarian, or don't be a bad vegetarian. And I went back to eating. I eat chicken and I eat fish. I don't eat red meat. That's my choice. You know. But in a way, I realize I'm eating something where that chicken ate an awful lot of grain to get that chicken. And if I'd eaten the grain instead of the chicken, life would have been bland, but I would have grain to spare, you know, because it's a more efficient way of eating. Last thing, sources of energy. Energy was created in the Big Bang. So Big Bang, 14.6 billion years ago, mysterious, energy just out of nothing. Space out of nothing. It was not that there was an empty universe before and the bang happened in it. There was nothing before and the bang happened. And after the bang, once the energy was there, it started creating space. And if that sounds weird, it is weird. It's unimaginable. So the Big Bang, the resulting expansion of the universe together with a condensation of matter from energy. So particles of matter were originally energy and they just condensed out. That's a really hard thing to do, but it happened. Established gravitational potential energy. So we have gravitational potential energy because we have mass in different places. So our gravitational potential energy comes from the Big Bang. And also kinetic energy. Our planets are moving. That's kinetic energy. So they really come from the Big Bang. Gravitational pull resulted from the separation of matter, drives nuclear fusion processes that heat the sun and the stars. Without matter, we would not have fusion. Without fusion, no stars. Our sun emits solar energy, which drives photosynthesis and ocean currents and atmospheric winds and transfer of moisture from low-lying areas to high land masses, which gives us lakes and rivers and streams. To this extent, all fossil fuels, wind energy, hydro energy originates in solar. The life cycle of the early stars in the vicinity resulted in supernova explosions that created heavy elements, and these enable nuclear fission processes. So your nuclear power plant is the result of star formation. Heat generated during the collapse and dust of globular nebula, of gas nebula that created our solar system, still warms the Earth's interior, and we can get geothermal energy. Electricity, and so what I want to say to that is, it's all about the Big Bang. And for us, it's all about natural forms of energy, which get converted over time. And the problem is, we tend to go for what's available that has a lot of energy density. And so we tend to go for fossil fuels. And the problem with fossil fuels is that we're undoing a lot of chemistry that the Earth took many, many millions of years to make. We're 4.6 billion years old. This is our galaxy, 4.6 billion years old. And there was a lot of chemistry took place in that time. The atmosphere did change. We took a lot of carbon dioxide out of the atmosphere by growing super huge trees, and that's the formation of your oil and your coal, basically. And over 100 years or so, maybe 150 years, we're undoing that, and it took millions of years to form those layers. So we're rapidly changing what happens in the Earth. But we need the energy. And so we look at these different things. There's the natural ones like the wind, people cheer, and the things like the dams and the hydro. Well, you cheer if you don't happen to live in that valley. If your house doesn't get flooded, it is a bit of a hit or miss thing with hydro. And we have nuclear, which is high technology. Can I ask you a question? What do you think? Do you think a typical nuclear power station is more or less efficient than a modern coal-fired power station? Which do you think is more efficient, the nuclear or the coal-fired power station? What do you think? Which do you think is most modern? Which is, new technology?
The nuclear, I think.
Yeah, nuclear. I mean, nuclear's post-Second World War power stations from coal, 1910, 1920, old technology. So for many years, I just assumed that the nuclear power stations must be more efficient. Okay, less efficient. They are less efficient than a coal power station. Because for various reasons, very, very predictable reasons, they're less efficient. Not by much. It's basically maybe 35 versus 30, something like that, but it's still less efficient. And it's hard to see how you can get around that. It's a different fuel, it's a different technology, but it still has this problem about the being very inefficient, really. There's a sun out there, which is a nuclear fusion process. It's dangerous. They talk about doing nuclear fusion on Earth and that it's not dangerous. Not really true. True, the products of nuclear fusion is helium. Helium's not that bad. So, kind of fine, really. The problem is it's such an intense form of radiation that it tends to irradiate the building it's made out of, which then becomes radioactive. So it's like, it's not that there's no... I read a book and it talked about the dirty little secret about nuclear fusion is if you do manage to do it on a building, then that building's going to be radioactive and you're going to have to bury the building, you know, at some point. So it's not without its risks. But there's a sun, which is 93 million miles away. And it sends out cosmic ray particles, which are dangerous. But we have a magnetic field which protects us from the cosmic rays. Otherwise, we wouldn't have developed. And it sends this energy to us in the form of light. And we can just collect it. And it just seems to me, I'm now convinced that natural forms of energy, that's basically wind, because that's the sun sending us its energy and the wind giving it to us. Or geothermal, which is the old radioactivity of the Earth, which is the old latent heat of the Earth, and the Earth is giving it to us. Or hydro. I don't particularly like building dams because it does flood people's valleys, but you can have basically water wheels in dams. Tidal energy. But then solar. In Florida, on a summer's day, in the day, 1,000 watts per square meter. It's a phenomenal amount of energy. If you could see the brightness of it, if you could look at it and look at objective level, then you look up and you don't see much, but if you could see it, how much energy has been produced, it's a tremendous amount of energy. Now, it's not there all the time, but that doesn't matter. It's there enough of the time we can store it, we can do stuff with it. And I think that's something that your generations are going to have to face. Because, you know, I mean, frankly, even if I have another 25 to 30 years, which at my age is like less likely, it won't really bite in that time. But for you and for your kids, it gets quite serious. We could really mess up the place in a whole bunch of unwise decisions. So think in terms of having the small footprint on the land and realize that energy companies sell energy. Why do they care which form it comes in? I mean, if it takes this amount of people to produce energy using one technology, the chances are it'll take a similar amount of people to produce energy using another technology. They're still going to have to maintain the wires. They're still going to have to get new buildings. They're still going to have to repair the solar farms. And it's going to be, it's not that it's going to decimate the economy. I don't believe anyway. You got a comment?
Oh. Is it the cost of like what makes the energy initially? Like right now it's cheaper for them?
Not these days. It used to be, but not these days. And to some extent, you know, yeah, I could make you the cheapest car possible and you wouldn't want it. You know, so as a consumer, I can give you the cheapest electricity possible, but do you want it? I mean, it's that kind of, I think it's tradition. You know, in some European countries, they would not think of building a huge power station. They'd just not even think it because it's not their tradition. And I think we just have and it's not that people are mean, and it's not that they are evil, it's just that they feel responsibility to go with what they know works. And when you're asking them to throw all that to one side and do something new, you know, me embracing technology has been the hardest thing. because you find it doesn't work sometimes, and you go, to heck with it, I'm not going to do it. And, you know, that stops progress, you know. So I used to get frustrated by this and say, they should just change things. But I'm not so convinced now. Now I think it's the very decent people are just doing what they think is right. But they've not got the same perspective that I have as a customer, you know. And I think it takes having those conversations and trying new things. Just like, you know, every utility company having a solar farm and learning that technology and finding that it is reliable and finding that, well, this is how you make it reliable. I think it makes a huge difference, I think. And I think, but the problem is I think that time is rushing forwards. So anyway, so take care of this when I'm gone. You can just, you know, remember this conversation and sort it out. So electricity is a clever way of transporting energy from one place to another, but it's not a primal source of energy in its own right. Electricity is like a delivery system. It's kind of like, you know, chemical energy that we're just... I mean, it's ironic. We burn fuel to make electricity to heat our houses. You know, you could have just burnt the fuel in a way. That's what we used to do. And the reason we stopped was because it polluted the heck out of the place. When I was a little boy, all those movies you see about London and the fog, which I thought was a natural phenomenon, was because everybody was burning coal-fired fireplaces in their homes. And it would just blanket the place. So when I was a little boy, I remember going to school with a scarf wrapped around my neck, and you could see the two little soot holes where my nostrils were and a little one for my mouth because it was just so covered in, the whole city was covered in smog. And again, you think it's natural. And then they bring in the Clean Air Act that says nobody can have a fireplace like that. So people go to gas and they go to electricity and stuff like that. And the gas becomes cheaper, etc. And suddenly no one's burning coal. And you go for years and you go, there's not been a smog for years. And then they sandblast all the black buildings, and all the black buildings are sandstone. And you don't recognize the buildings. You go past the town hall, it's like, hold on, what did they do to the town? Did they paint it? No, they just cleaned it. They made it the way it was before it got dirty. And I used to get bronchitis every spring. You get bronchitis. You have coughing. You cough your lung up. And not me, everybody. We all had, you got bronchitis. Green phlegm, you got bronchitis. You know, it's spring. What do you expect? And then my brother says he's not had bronchitis in years. And it's because he was living in a polluted place, and you just take it as normal because that's what you're born into. So don't let it happen again. Okay. I'm sorry I'm going on a bit. I'll stop this.